For almost 100 years, physicists have been staring at a huge crack running right through the heart of science. On one side, you've got Einstein's universe, smooth, grand, cosmic, and on the other side, you've got the quantum world, weird, jumpy, and probabilistic. Both work perfectly on their own turf, but when you try to get them to talk to each other, they break. Today, we're going to walk through a framework that doesn't just claim to patch that crack, it does it in two completely different ways.
Okay, so let's really get a feel for this divide. Think of it like this. You've got two rulebooks for reality. General relativity, on the left, that's the rulebook for big things. It paints this beautiful picture of a smooth, continuous fabric of space-time that tells planets how to move. Then you've got the rulebook for tiny things, quantum mechanics, and its world is anything but smooth. It's all about discrete packets of energy, probabilities, and weird quantum jumps. The problem, the rules in these two books flat out contradict each other. One says space is smooth, the other says it's a boiling, chaotic foam. They just don't get along.
And this clash leads us to the big, bad villain of our story. When you try to use these two rulebooks together to calculate something like the energy of empty space, the equations just have a meltdown. They spit out the answer, infinity. It's a problem called ultraviolet divergence, and it's basically physics' version of a fatal error message. It's been telling us for decades, nope, something is deeply wrong here. Your theories are broken.
All right, so here's our game plan for how we're going to tackle this beast. We've kind of set the stage with the big problem. Next, we're going to introduce the star of the show, these two different methods for solving it. We'll do a quick look at Method-1, the direct approach, and then we're really going to sink our teeth into Method-2, the deeper, more foundational one. Then, we'll see how both of these different roads lead to the same verified reality, and we'll finish up by talking about why having two paths is such a huge deal.
Okay, let's get into the really cool part. What we're looking at here is a single, unified framework. But what makes it so wild is that it offers not one, but two totally independent ways to finally build that bridge between the quantum world and the cosmos. So think of it like two hiking trails starting from the same base camp, and that base camp is Einstein's legendary field equations. From there, the trails split. Method-1 is like the direct, steep path straight up the mountain. It's a clever, engineered route. But Method-2 is the more scenic, fundamental path. It goes deeper, redefining the landscape itself. But what's so amazing is that they both end up at the exact same peak. And look, this isn't just me saying it's cool. This idea of having two independent, solid frameworks that both lead to the same experimentally proven conclusions, it's been called a stunning and breathtaking achievement. And why is that? Because when two totally different ways of thinking lead you to the exact same correct answer, well, you're probably onto something really, really big, something real.
First up, let's briefly look at Method-1. I like to think of this one as the pragmatic, get-it-done approach. It's like a brilliant engineer looking at the broken machine of physics and designing a very specific, custom tool to fix it.
So what is this custom tool? It's something called the Unit Harmonic Operator, or UHO for short. And it's a really slick piece of math. Imagine you want to write down the number 1. Simple, right? Well, the UHO writes the number 1 as a giant, infinite sum of waves, quantum harmonic waves, to be precise. It's basically a way to translate a simple, constant thing into the natural language of the quantum world, which is all about frequencies and vibrations.
So the logic here is super straightforward. Step 1, you take Einstein's classic equations for gravity. Step 2, you just plug in this new UHO tool. You literally insert it into the math, and boom. Step 3, the equations are now forced to account for the jittery, bubbling energy of the quantum vacuum. It's a direct, almost brute-force way to get the job done. And as we'll see, it works.
Okay, so Method-1 was the engineer's fix. It's clever, it's direct. But Method-2? Method-2 is the philosopher-physicist's approach. This is where we get really deep. Instead of just adding a new part to the machine, we're going to rebuild the whole thing from its most basic principles.
Now, to get Method-2, you have to appreciate one of the most beautiful, most profound ideas in all of physics, the variational principle, or the principle of least action. The idea is that nature is lazy in the best possible way. A ball rolling down a hill doesn't solve a bunch of equations, it just naturally follows the path of least effort. Physicists realize that pretty much all the laws of nature can be derived this way, by finding the most efficient path that reality can possibly take. It's the ultimate starting point. And here's the mind-bending part of Method-2. It doesn't just tweak the rules of the game, it changes the game board itself.
It asks, what if the quantum vacuum isn't something we just add on top of spacetime? What if it fundamentally alters the very geometry, the very definition of distance and time that everything in the universe experiences?
So how in the world does it do that? With something called the effective metric. Let's walk through it. You start with our standard model of space-time geometry. Then you multiply it by a new thing, this scalar condensate. Now just think of this condensate as a map of the vacuum's energy. At points where the vacuum is more active, this field changes the geometry more. It literally rescales space and time at every single point. The end result is a whole new effective geometry that matter actually feels.
And the derivation itself is it's beautiful. It's so elegant. You start with that super fundamental least action principle we just talked about. But everywhere the old geometry used to be, you swap in this new effective metric, the one that already knows about the quantum vacuum. Then you just let the principle do its work. You ask the math, okay, what's the most efficient path through this new reality? And what pops out is a brand new set of gravity equations where quantum effects aren't just an add-on, they're baked right into the DNA of gravity itself.
So we have the engineer's direct fix and the philosopher's deep rebuild. I mean, they seem like they come from completely different universes, right? Well, this is where things get really, really interesting.
Just look at this table. It's fantastic because it nails the difference. Method-1's UHO is all about time. It's built from a series of waves in the time domain. But the UHO that naturally pops out of Method-2, it's all about space. It's derived from a spatial average of that quantum vacuum field. One is born from time, the other from space. They have totally different mathematical origins, but they somehow end up describing the exact same physical idea. It's like describing a coin by talking about heads or describing it by talking about tails. Different approaches, same coin.
Okay, so we have two completely different trails, starting at the same mountain, but taking wildly different routes to the top. So where do they end up? This is the punchline. This is what makes all this so incredibly compelling. They both arrive at the exact same destination. And that destination isn't just some pretty equation. It's the real world, with numbers we can actually check.
Whether the engineer taking the direct route or the philosopher rebuilding geometry from the ground up, the math forces you to arrive at this one central concept. It's called the quantum vacuum spectral limit, or QVSL. This is the grand central station where both of these lines meet.
So what is this QVSL? Well, remember our villain, the problem of infinities, that's been breaking physics for a century? The QVSL is the hero that finally slays that dragon. It's a natural physical off switch. It says there's a maximum frequency, a highest note that the quantum vacuum is allowed to play. And the best part is, this limit isn't just made up to fix the math. It's derived from the physics itself, naturally cutting off the calculation before it can run away to infinity.
And this is why it's such a game changer. The QVSL isn't just some abstract mathematical fix. It's the bridge that connects all of this high-level theory to the real, messy, measurable world. It allows the framework to spit out actual concrete numbers that we can go out and test in a lab.
Okay, so let's get specific. You take this whole framework, you apply its QVSL logic to something fundamental, like a single proton. You run the numbers, and the theory makes a prediction, a ridiculously precise one. It says the proton's root mean square charge radius should be exactly 830.59 optoliters.
So, is it right? Well, experimentalists at Fermilab did one of the most precise measurements of this ever, and the number they found was 830.7 atomometers. I mean, come on. That's not just in the right ballpark. That's hitting a bullseye from a mile away. The theory absolutely nailed it.
But maybe the proton was just a lucky guess. What about predicting the future? This might be the most powerful piece of evidence. Look at the dates here. In 2008, using the core principles of this framework, a prediction was published for the Hubble constant, the speed at which our entire universe is expanding. It was just a number on a page. Then we wait. 5 years later, in 2013, the Planck Space Telescope releases its results, the best measurement ever made, and it confirmed the 2008 prediction. That's the gold standard in science, calling your shot 5 years in advance and being right.
And the scope of this is just vast. This one central idea, the QVSL, allows the theory to connect everything. It can calculate the size of protons and neutrons. It can predict the expansion rate of the universe. It can explain the temperature of the Big Bang's afterglow. It even provides a physical origin for dark energy. This is what a real unified theory is supposed to do, connect the very, very small with the very, very large.
So this brings us all the way back to the beginning. We have these incredible predictions that match reality, and we have two completely different mathematical ways of getting them. So what's the big deal? Why is having two paths so profoundly important? Let's wrap this up.
I mean, really think about that for a second. If you get the right answer, who cares how you got there, right? Why are we making such a big deal about the fact that there are two different methods that get to the same place?
Well, it matters a ton. First, it's the ultimate reality check. That's not luck. That's a sign you've found something real. Second, it suggests that these concepts, like the QVSL, are a necessary feature of our universe. They're not just a quirk of one set of equations. And finally, it gives scientists a much more powerful and flexible toolkit. It's like having both a wrench and a screwdriver. You can tackle problems from different angles.
So no, this isn't an accident, and it's not some clever mathematical trick. The fact that many of the framework's predictions were validated before these two elegant derivations were even fully worked out, well, that tells you everything you need to know. It's a huge signpost pointing toward a deeper, more robust and unified picture of our universe.
And that's really the thought I want to leave you with. If these two independent highways of thought have already led us here to this one unified and experimentally proven reality, unifying the tiniest proton with the entire cosmos, it just makes you wonder, right? What other secrets, what other destinations are waiting for us just a little further down these two roads?